Welcome to class of Satellite and Radar Systems. This is Unit 2, Part 2. So, we continue with our lecture about satellite subsystems. So, these are the contents for today's lecture. We'll have a brief overview of satellite subsystems, which we have covered in the previous lecture. We'll talk about power systems, antenna subsystems, and transponders. So, first of all, let's go into a brief of what we have studied. What are satellite subsystems? Subsystems are the supporting system in satellite which helps satellite to achieve all those things that are required by a satellite to do, right? So, if we talk about maintaining a microwave communication system in orbit in space, it is not just a simple process, it's a complex process, right? And the cost by which we launch a satellite and making a satellite makes it a big project. So, how do we earn from it? Through the revenues by selling the services. Now, if we make our satellite remain in its orbit, for a communication satellite, the average lifetime is approximately 15 years. So, in these 15 years, we earn the revenue from it by selling the services. Like we do pay for the DTH services, we do pay for services like mobile communication, the internet, right? These all are the services that user pays, and these are the services that are provided by satellite. So, subsystems are needed on a satellite to support its primary mission of communication and further to keep satellite in its exact rotatory position in orbit. So, we need supporting system. If we need to keep our satellite in orbit for 15 years and do the same functionality for uninterrupted services for 15 years, we need some supporting system that will help it, right? So, a subsystem that must exist in the communication satellite, it enables the spacecraft to communicate with the ground stations that control the satellite and to deliver the data that the mission requires. So, this shows the complete picture of a satellite with the supporting subsystems, right? So, this is a typical satellite with bus and payload separation, right? We have the bus, the rocket that carries the satellite to the orbit, and the payload, that is the actual communication part of the satellite. So, we do have here GPS antenna, X-band antenna, S-band antenna, image payload, camera, and it is equipped with more of the things like solar panels, different antennas, right, processing system within it. So, this depicts a picture of a complete satellite subsystem. Solar arrays. Now, we are talking about power system, right? So, basically what are power systems? We know that the satellite present in an orbit should be operated continuously during its lifetime. So, satellite, what it requires? Satellite must be equipped with solar panels that will obtain energy from sun and that will be used for working of the satellite. So, we need solar panels, right? We need uninterrupted power supply. So, sun is the only source out there in space, but we need to equip our satellite with batteries also for conditions like solar eclipse or when the solar panels doesn't work properly. So, there must be a backup with it. So, power system is a vital subsystem which provides the power required for working of a satellite, right? We have transponders, we have antennas, we have signal processing within it, amplifiers, they do need some power input, right, for proper functioning. So, mainly the solar cells and rechargeable batteries are used in these systems. All communication satellites obtain their electrical power from solar cells which convert incident sunlight into electrical energy. right? The satellite must carry batteries to power the subsystems during launch and during eclipses. So here comes the role of batteries as well. So it must have solar panel for continuous supply, and for emergency situation it must have some batteries within it, right? So if we talk about how solar cells work in space, the total vacuum of outer space at for everything we are taking reference of geostationary satellite, whether we take reference of the velocity or the position or the power it gains. Geostationary altitude, the radiation falling on a satellite has an intensity of 1.39 kilowatt per meter square, right? So this is the intensity. Now the complete energy that falls on solar cell, that doesn't get converted into electrical power. Every system has its efficiency. So when the solar cells are new, that is, we talk about beginning of life, in BOL their efficiency is around 20 to 25%, right? At end of life, EOL, it reduces to, it somehow reduces, right? Even in the very beginning, only 20 to 25% of the solar energy gets converted into electrical energy. These are some things that must be taken into consideration. How much power our satellite or proper functioning requires, and according to that we design our solar panel, or we make our satellite equipped with that amount of solar cells, right? Since sufficient power must be available at the end of life of the satellite to supply all the systems on board, about 15% extra area of solar cells is usually provided as an allowance for aging. So initially some portion of the solar cells is not operable, but at the end of life, just to counter the reduced efficiency, we make them operable, right? This is how we enable it. In a stabilized satellite, we remember the cylindrical structure of a satellite, which I'll be showing in next picture. It usually has a cylindrical body covered in solar cells. Completely it is covered by solar cells, right? Whereas in 3-axis stabilized, it has panels which get flared when the satellite goes into its exact orbit. So there is difference in the efficiency and functioning, how do they obtain energy and how it is converted, right? In 3-axis stabilized satellite, it can make better use of its solar cell area, because where the sun goes, it can tilt its panel, right? For solar cells, if we imagine the cylindrical structure, only a particular area, little portion of the complete drum will be visible to sun, whereas in 3-axis stabilized, the complete panel can be tilted facing the sun. So it is somewhat better in efficiency. Only 1/3 of the total area of solar cells is needed relative to a spinner. We can easily see that, right? So when it comes to which design is better in respect of power system efficiency, we would prefer 3-axis stabilized, saving the weight as well, right? Solar cells are the things that carries most of the weight of the satellite. So if we talk about solar arrays, there are 2 types of solar arrays that are used in satellite: cylindrical solar arrays and 3-axis stabilized, right? That we have just spoken. So these are the supporting pictures for it. We have seen it earlier as well. This is a cylindrical satellite. Solar cells are mounted all over its body. This is a 3-axis stabilized satellite. Here solar cells are mounted on its wings. So if we talk about some amount of power, like X power is needed. So if we compare these two, 1/3 of the solar cells here will be capable enough of for providing similar amount of power, because here we can say sun can be facing only few portion of the complete drum, whereas this can face the sun when and where required. So now if we talk about solar cells in detail, what kind of cells these are? These are a kind of photovoltaic cells, right? Light energy falls on it and it converts it into electrical energy, right? So spacecraft operating in the inner solar system usually rely on the use of photovoltaic solar panels to derive electricity from sunlight. Basically, the solar cells produce electrical power from incident sunlight. Therefore, solar cells are used primarily in order to provide power to other subsystems of satellite. We know that individual solar cells generate very less power, so in order to generate more power, group of cells that are present in an array form can be used, right? So what are the, now if we talk about rechargeable batteries, apart from solar cells, what are the like if we talk about solar arrays, in 1990s the solar arrays used in space primarily used crystalline silicon solar cells. These were our first choice. Later on, these were replaced by gallium arsenide based solar cells, right? So they have gallium arsenide has its own advantage, semiconductors have their own advantage, right? So these being favored over silicon because they have a higher efficiency and degrade more slowly. So we have increased lifetime than silicon in space radiation environment. We have to consider the point that environment is harsh over there. These are comparatively closer to sun, right? The most efficient solar cells currently in production are now multi-junction photovoltaic cells. So for now we have been talking about solar cells, the panels, what are these made up of. We switched from silicon to gallium arsenide, now we use multi-junction photovoltaic cells, right? So these are about solar cells and how do they look like in these two kinds of satellite. Now what about the emergency situations when there is solar eclipse or some or the solar panel, solar cells die? We need to equip our satellite with some rechargeable batteries that comes into operation when there is emergency. So during eclipse time, it is difficult to get the power from sunlight. So in that situation, the other subsystems get the power from rechargeable batteries. These batteries produce power to other subsystems during launching of the satellite also, right? So in general, these batteries charge due to excess current. So when they discharge, they get charged themselves, right? So we cannot equip our satellite with some batteries which will run forever. Batteries, they do discharge. So these are, we equip our satellite with rechargeable batteries. So if we talk about fixed satellite systems or fixed satellite services, they do require quite lesser energy, like 2 to 5 kilowatt of power. But if we talk about broadcast satellite systems, they need 10 to 12 kilowatts, right? So what is the solution for it? Lithium ion batteries. These are very much efficient. So latest battery technology presented by lithium ion systems that can provide a greater power density for longer periods of time and survive a greater depth of discharge. Even they discharge to greater depth, close to 10% or less than that, they still can be recharged. Although that is not preferable. If a battery dies below for a few percent, then it's difficult to get it recharged, but lithium batteries, they do withstand this thing, right? So lithium ion batteries are preferable one, although they are a little expensive, but the complete system that we are implanting is also very expensive, so we cannot compromise with the quality, or right? So that was all about power system. So far we have studied about attitude and orbit control in the previous lecture, telemetry tracking and command system. Now we have been studying about power system, then we'll be studying about antenna subsystems and the actual communication systems, right? Antennas are present in both satellite and earth station, receiving transmitting antenna at both ends. Why? The main role of satellite is to gather some information, transmit some information, so mainly does communication. So antennas are of utmost requirement. Now satellite antennas perform two types of function. These are receiving of signals which are coming from earth station and transmitting signals to one or more earth station. These are based on requirement, right? Satellites, they do have transceiver, right? They receive signal, they transmit signal. We know that the length of the satellite antennas is inversely proportional to the operating frequency. So the operating frequency has to be increased in order to reduce the length of the satellite antenna. So these are the basic relation between the frequency and wavelength and the distance, right? Therefore satellite antennas operate in the order of gigahertz frequency. So what are the common types of antennas that we use for satellite communication? We have wire antennas, horn antenna, array antenna, reflector antennas. These are the basic kind of antennas that we use for satellite communication, right? If we see, this picture shows how the antennas are mounted and how does it look like. This represents the solar arrays, right? We can see here it is equipped with omnidirectional antenna, KU band feed horn antenna, KU band antenna. So we have C band antenna. We have different antennas mounted for different frequencies, right? So in this picture we have tried to show a satellite is equipped with different antennas. So let's talk about the very common wire antenna. These are basic antennas, monopoles and dipoles. We all must have studied about these antennas, right? So the length is lambda by 2. This is dipole antennas, right? Half wave dipole antenna where the length is lambda by 2. Now wire antennas are suitable for covering its range of access and to provide signal strength in all directions. That means wire antennas are omnidirectional. So a very common, very basic kind of antenna, wire antenna, is used here, which will act as omnidirectional antenna. So this is how a wire antenna looks like. Next is horn antenna. Here the aperture at the end can be termed as aperture antenna, right? A simple waveguide, when it is flared at its end, it can be considered as a horn antenna. It's an example of an aperture antenna. This is used in satellites in order to cover more area on Earth. So these are horn antennas. They have their use in microwave frequency. These are the very famous kind of antenna. They are very popular and mostly used in microwave frequencies. The same feed horn can be used for both transmitting and receiving the signals. A device named duplexer which separates these two signals. This is how a horn antenna looks like. We can see a simple waveguide, a rectangular waveguide. When it is flared at its end, it looks like a horn. It somehow provides the waves some direction. If we talk about array antennas, this will be group of antennas. It is exactly laying down antennas in particular structure so that it fulfills some need. Like we need output at a particular area, or we need better coverage, then we instead of using a single antenna, we'll use array of antenna, right? These are basically used in satellites to form multiple beams from signal aperture, right? So they are used for multiple beams. We can see group of antennas, right? Now if we talk about reflector antennas, these are suitable for producing beams which have more signal strength in one particular direction. That means these are highly directional antennas. So parabolic reflectors, they increase the gain of the antennas in satellite communication systems. Hence these are used in telecommunication. Reflector antennas are basically used for telecommunication, like DTH services. We all have direct to home. For direct to home services, we all have DTH mounted on our rooftop, so they do capture signal from satellites. So these are basically parabolic reflectors or reflector antennas. It is used for transmitting a signal. The signal from the feed comes out of the dipole or a horn antenna to focus the wave onto the parabola. It means that the waves come out of the focal point and strikes the paraboloid reflector. This wave now gets reflected as collimated wavefront. Right, so these are the basic functioning and working of reflector antennas, which we can go into detail if you want. So this is how a reflector antenna looks like. Everyone must have seen it. Now the third thing that we talk about is about transponders. This is the most important or the basic part of an antenna for which we use of a satellite, for which we use satellite, right? We use satellites for communication. It does some work and that needs to be communicated. How it gets communicated? With the help of transceivers. We have transmitters and receivers, the complete system that is called as transponder. The subsystem which provides the connecting link between transmitting and receiving antennas of a satellite is known as a transponder. It is one of the most important subsystem of a space segment subsystem. It provides the connecting link between transmitting and receiving antenna. The main communication, right, is accomplished by the help of transponders. So transponders, they do perform the functions of both transmitter and receiver in a satellite. We can call them responder as well. Hence the word transponder is obtained by the combining few letters of the words transmitter and responder, that is ponder. Right? This is how transponder word comes into existence. So if we talk about basic block diagram of a transponder, we do have satellite antenna from which it receives signal or transmits signals. With the help of a duplexer, the first block in any communication receiver is a low noise amplifier that will cut down the noise and that will amplify the signal received, right? So it can be called as pre-selector as well. Then we have, so the antenna must be RF frequency antenna, right? We have a duplexer here because it will be transmitting as well as receiving. We can add on few things, like we can have pre-selector that will select the wave, then low noise amplifier, it will remove cut down noise, amplify the actual signal, then carrier processor, power amplifier. This will be a complete thing. If we have studied about super heterodyne receiver, the mixer part will be here, the down conversion. With the help of a local oscillator, we might generate carrier locally here. We'll be getting RF frequency here, and both when they'll be intermixed here, we'll be getting various frequencies, right? So from RF range, we'll convert it into IF frequency, intermediate frequency, and this carrier processor will be a whole lot of combination of different things. A product modulator, maybe band pass filters, IF amplifier. So it will be composed of whole lot of things. Then actual demodulator, right? So the complete receiver thing will be here, and of course we need power amplifier, and finally it goes to final destination, right? We can go into detail of this, like in communication system we must have had studied. So if we talk about working of each block, duplexer is a two-way microwave gate. It receives uplink signal from the satellite antenna and transmits down signal to the satellite antenna. We have a low noise amplifier. It amplifies the weak received signal. We have a carrier processor. It performs the frequency down conversion of the received signal. So this block determines the type of transponder, which kind of it is, a bent pipe or single conversion, double conversion transponder. The details of transponder will take separate time. Now we have power amplifier that amplifies the power of frequency down converted signal to the required level. So we have RF frequency, then IF frequency, then the actual frequency. we have basically two types of transponder, bend type transponder and regenerative transponders. What's the basic difference between these two? A bent pipe transponder, it receives microwave frequency signal and it converts the frequency of the input signal into RF frequency and then amplifies it, right? So this is how basically a transponder, a simple transponder works. Receive microwave frequency, right? Converts the frequency of input signal to RF, then amplify. It is also called as a repeater and conventional transponder. It is suitable for both analog and digital signal. So regenerative transponders. What are regenerative transponders? It has something in addition to bent pipe transponder. A simple bent pipe transponder does perform frequency translation and amplification, whereas a regenerative transponder, along with these two functionalities, it will perform the demodulation as well. So this will perform the complete task of a super heterodyne receiver. It will do the frequency translation, that is down conversion. It will have a product modulator. It will convert it into IF frequency, then into the user readable frequency. It performs the amplification, and the actual demodulation is also carried out here. So a regenerative transponder is also called as a processing transponder. It is suitable only for digital signals, and the main advantage of this regenerative transponder is improvement in signal to noise ratio. So we have a greater value of SNR, that is average signal power to average noise power is improved here. So we get better quality of signal here. This is how a simplified single conversion transponder, a bent pipe transponder, looks like. Like a receiver has a receiving antenna, low noise amplifier, and a receiver will have series of band pass filters and down converters. It has a band pass filter, it has a down converter, the RF frequency comes from here, locally generated carrier will go here, it will down convert the signal and convert it into IF range. Then we have band pass filters, then again we have amplifiers, low power amplifiers, high power amplifiers as per the requirement. This is 6 to 4 gigahertz, 6/4, this is something of correction, we can do that. This is 6/4 gigahertz, right? So this is simplified double conversion transponder. This is for 14/11 gigahertz band, right? So we have that single conversion transponder in double arrangement. It is the same thing as it has worked. This is how onboard processing transponder looks like. We have receiver, the super heterodyne receiver, the demodulator, we have error correction here, we have onboard processor, we have forward error correction, then modulator, then transmitter. For receiver we have demodulation, for the transmitter side we do have, for receiver we have demodulation, for transmitter we need to perform modulation first, then we do transmit. So this is how a simple or a basic communication system works like. Thank you. These are the references used.